My name is Maximilian Pittner from Robert Bosch and University of Lübeck, and I will present our research paper 3D-SpLineNet, 3D traffic line detection using parametric spline representations. In this work, we focus on the traffic line representation. In recent years, many lane detection methods used anchor-based representations, which show limitations if the lane deviates severely from the straight anchor line. Parametric representations, in contrast, model traffic lines as continuous functions directly. However, so far, polynomials were used mainly that do not serve as an appropriate lane model for typical road shapes. Instead, we decided to choose B-splines as our representation, leveraging the benefits of parametric representations and the capability to model typical road geometries. While former methods that used parametric representations modeled lanes merely as a simple function either in front or top view, we proposed a 3D curve representation instead. For this, we modeled the lateral x and height z direction as parametric functions. Eta is a normalization vector containing the maximum expected range. More precisely, we model x and z using B-splines, where alpha and beta describe the control points. Since we're so far modeling curves of infinite length, we also have to restrict the curve argument to a domain given by the start and end point TS/TE. Since we're interested in multiple lines, we also model an existence probability P for each of M-line proposals. These parameters for M-line proposals are predicted by our network 3D-SpLineNet. Inspired by GenLayNet, our architecture consists of an EarthNet backbone, an IPM layer, and a fully convolutional detection head. While GenLayNet decouples the problem into line segmentation and detection, we apply certain modifications to make the whole network trainable end-to-end on the detection task. Here we want to elaborate on the main differences between anchor-based and parametric representations. Illustrated as blue points is the real ground truth, and in green, the truth signal used for training regression. On the left side, the green vertical line depicts a straight line anchor, and the dashed horizontal lines show the predefined positions at which the anchor offsets are computed. While for anchor-based methods, the regression is only computed at predefined positions, a short line, as illustrated here, is hardly learnable. In contrast, with parametric approaches, the ground truth points used for regression can be sampled along the entire line. Besides, as the regression for anchor-based approaches is evaluated at predefined positions, the ground truth has to be interpolated at these locations, inducing geometric errors. Parametric approaches instead use the ground truth directly. Also, many anchor-based methods use a static reference point-based matching to assign ground truth to the anchors, which ignores lines not passing the reference. Ours instead considers all appearing lines and matches them to the proposals in an optimized manner. We evaluate our approach on a synthetic dataset named Apollo 3D Lane Synthetic and compare it to two anchor-based approaches, 3D-LaneNet and GenLayNet. Here we show the performance of each method on the challenging rare scenes test set. Note that our 3D-SpLineNet outperforms the other methods with respect to the detection scores by a large amount and also achieves lowest geometric errors with respect to most criteria. Since our method does not require time-consuming post-processing, it also achieves lowest runtime. For a qualitative comparison, we show prediction examples from all test sets. The ground truth is illustrated in blue, predictions from GenLayNet in green, and from our 3D-SpLineNet in red. As the illustrations show, our method manages to better model the ground truth lane geometry in simple as well as in more complex scenarios. In summary, our main contributions include a new representation to model 3D lanes with parametric B-splines and our end-to-end trainable detection network 3D-SpLineNet achieving state-of-the-art performance. In future, we will investigate ways to improve far-range height estimation. Due to the lack of real 3D ground truth, we will also investigate weakly supervised approaches that can learn from 2D ground truth as well. We thank all listeners for their attention.